So in this video, we are going to talk about LoRa, low rank adaptation. It's about parameter efficient fine-tuning your LLM. So first we are going to talk about why and how to do fine-tuning. And there are different kind of ways you can do the fine-tuning. And we will drill down a little bit into the theory. So when you will come to the code, when you are looking at the Python code, you will understand exactly what these parameters mean in the Python code. Because I have seen many YouTube videos where they talk about fine-tuning a model. They will just show you 4 lines of Python code and that's about it. But there's so much behind that. All those parameters has to be fine-tuned properly to do a fine-tuning of an LLM. And there's a very few videos I have seen where they go little depth into it to talk about the parameter. So that's what I'm going to try here to talk a little bit about the theory. And then in the end, we will look at the Python code. So let's look at what is a base LLM model is. So let's keep things very simple and imagine this LLM is a brilliant, highly educated university graduate who has read huge portion of the internet. Just imagine that this LLM knows about everything possible, everything generic, and then we will go in our journey as we will start fine-tuning, we will see how we can change this LLM. So before we move ahead, let me give you an idea about the size of these LLM. So the tiny and small model will have around 10 billion parameters, and they will be efficient for a very specific task or for edge devices. They can be loaded in a mobile phone. They are faster to train and run, but may lack depth in general intelligence when the parameter is less than 10 billion. Okay. And medium models are 10 to 100 billion parameters. That's the sweet spot for many applications. So that's where we balance the capability with practicality. Common in open source releases, you will find these medium size models where the size is 10 to 100 billion parameters. And large models, they will be 100 to 500 billion parameters. They are the high performance for broad tasks like creative writing or analysis, but very resource intensive. As you can imagine, there's about 500 billion parameters are there. And the large language model, the ultra large, which we call now, basically they are the large, they are not ultra large anymore. They are into trillions. They have trillions of parameter. And here's a table where you can see the GPT-4 is around 1.5 trillion parameters there. For Gemini, they don't have it printed anywhere, but approximately they will be also in couple of trillion parameters. As you can see, GPT-3 is 175 billion, and GPT-2, which was almost useless, was having about 1.5 billion parameters. So of course I say it useless because it was not very earth-shaking, and it is not able to show what AI can do. But after GPT-3, the whole world changed because with 175 billion parameters, it was a huge breakthrough in 2020. Now, let's talk about fine-tuning. Now, let's take this analogy to the next level, where we have taken this brilliant university graduate and putting him or her through this medical school to become a doctor. Now, you are not going to reteach them English or basic math. You are giving them a specialized knowledge. So that is what is full fine-tuning is all about. So the process of taking a pre-trained base model and continuing its training on a smaller, specific, and high quality data set. So this is the most straightforward method. You take the pre-trained LLM and update all of its weights while training on your new task-specific data. The entire model is unfrozen and every parameter is updated via backpropagation. It's essential a continuation of the pre-training process, but with a focused data set and a specific objective like classification and summarization. So what is the goal here? Goal here is to specialize the model knowledge or to make it follow a specific style, format, or personality. Like as we are showing in our example, now this college graduate knows everything about the medical science. So he is becoming a doctor. So how it works? You show the model example of your specific task, like thousands of questions, answers pair about medical diagnosis. And the model adjusts its internal weights parameters to get better at that given specific task. So now a new full-size model that is an expert in a fine-tuned domain, it is still as large as the base model because you have modified the original weights. It has a very high performance. You can achieve the best possible performance as it allows the model to adjust completely to the new data. Here again, I'm showing you billions of parameters. As you can see, even tiny and small have billions of parameters, but we are not talking about here trillions of parameters. The reason is, retraining or fine tuning these big models like GPT-4 and 3, first of all, you'll not have access to them completely. Second, it will be extremely expensive. Each run goes in hundreds of millions of dollars. So we will see what a kind of LLM, the small LLM, the open source LLM, you can pick it up and you can fine tune them for a very specific task. And disadvantage of this full fine-tuning is cost. Of course, it requires immense GPU, memory. Fine-tuning a 70 billion parameter model requires multiple high-end GPUs like A100 or H100. And the next problem can be they have a catastrophic problem of forgetting. So these models might forget some of the general knowledge from its pre-training phase as it over-specializes on the new task. So they may forget about things which they were trained on, where millions of dollars were spent to train them, and they just forget all that and just become very specific to your data set. So that's a risk. It can be overfitting there. And of course, the next problem is the storage inefficiency. So for every new task, you must store a complete multi-billion parameter copy of the model. And these models are updated all the time. They are very quick to be updated. So imagine if you are creating a fine-tuning a model and it gets updated every second month, then you have to be updating yourself also and pre-training again. So that's a big downside of it, the storage inefficiency. And the process can be computationally very expensive, create a completely large copy of the model for every new task. There can be some use cases where if you are in a very particular vertical business, say law or bank or say a call center, and you just take one large model and train them on your data so you don't have to keep training them again and again. So that can be one of the use case for this kind of fine tuning. So here we are showing you 4 fine tuning different methods. So out of these 4, the best one is the LoRa rank decomposition, and we'll be focusing on that mostly because the industry is done a lot of trial and error, and after a lot of research, and all of these have multiple papers came out of different research, we have realized the rank decomposition is the best one. And let's talk very quickly a little bit about all of these, like fine-tune last layer. So, so this one here, as you can see, this is a fine-tuning approach where only the output layer of a pre-trained model is modified and trained for a specific downstream task, while the rest of the model parameters, they remain fixed. They remain frozen, unchanged. So a very task-specific head refers to a small, customizable neural network layer or module added on top of the pre-trained model to handle the target task, such as classification, regression, or generations. For example, in a transformer model like BERT, you might add a linear layer for sentimental classification and train only that layer using task-specific data, right? So how it works, the pre-trained model acts as a fixed feature extractor, this pre-trained model, which is little light in color here. Now, during training, the gradients are computed only for the task-specific head, and backpropagation doesn't affect the earlier layer. So here we just realize that only the head is trained and the whole the neural network or the LLM as such is left untouched. So the limitation of it is it may not perform well if the pre-trained model isn't well aligned with the new task. As deeper adaptation aren't made, it's less flexible than full fine-tuning. So a couple of use cases where you can use something like that is for image classification. Adding a head to pre-train ResNet or NLP tasks like text classification. So the next one is adapter layer. So adapter layers are a technique to introduce additional layers, as you can see the dark layer here, into a pre-trained model without altering the original weight significantly. So the whole model stays as is, and we just insert the adapter layer. We'll talk more about what these layers mean and how they come in the picture in fine-tuning later. But just understand that there are different layers in this transformer or this neural network of LLM, and we just change some layer. So these layers are the small trainable modules inserted between the existing layer of the model. So they allow the model to adapt to a new task by learning task-specific features while keeping the majority of pre-trained models parameter frozen. So this approach is efficient in terms of memory and computational, as you can see that, making it very suitable for a scenario with limited training data or when computational resources are constrained. So these adapters, as you can see the dark layer, the adapters, they are added after attention or feed forward sublayer in transformer. Again, we will see a little bit more about layer, but as you understand, these transformers, they have this attention layer and feed forward sublayers, etc. So these adapters are added there. So the biggest benefit, as you can see, is adds very few parameters, like 1 to 3% of the model size, enables multitasking learning. So one adapter per task can be created, and it's reversible. Adapters can be removed or revert to the original model. It is efficient for large models where full fine-tuning is impractical. So the biggest limitation we have seen is the performance might be slightly lower than full fine-tuning on complex tasks. And inserting adapters can add minor inference overhead. It's saying minor inference overhead, but that's what I'm reading in many papers, that inference becomes slow. And the use case is multi-domain adoption in NLP, like fine-tuning GPTs for multiple language or different tasks or vision models. Like there's a model called VIT, V-I-T. And the next one is prefix tuning. As you can see here, Prefix tuning is a method where fixed length prefix tokens are added to the input sequence of each layer of a pre-trained model. These prefix tokens are trainable parameters that act as a steering mechanism, guiding the model behavior for a very specific task. So instead of adjusting the entire model, prefix tuning modifies how the model processes input by focusing on these prefix tokens, which can lead to efficient learning with minimal change to the original model weights. So instead of adjusting the entire model, prefix tuning modifies how the model processes input by focusing on these prefix tokens, which can lead to efficient learning with minimal changes to the original model weight. And the benefit is, as you can see, it's add very few parameters. So the next one is prefix tuning. So prefix tuning is a method where a fixed length prefix tokens are added to the input sequence for each layer of a pre-trained model. So there are two kinds of prefix tuning. One is prompt tuning and a prefix tuning. So prompt tuning, a small sequence of trainable vector soft prompt is pre-appended to the input embedding. The model learns the optimal prompt to guide its behavior for a specific task. As you can see here, this is called prompt tuning. And the next one is prefix tuning. It is a more powerful version where trainable prefix vectors are added not just at the input, but to the keys and value in each attention layer of the transformer. So this is how we do the prefix tuning. So now let's talk about the adapters. They are the more modern and efficient way to achieve the same goal as fine-tuning. This is a key technique in parameter efficient fine-tuning. It's called PEFT, parameter efficient fine-tuning. So coming back to our analogy, which we were using from the beginning, here, as you can see, we have this graduate, and we just want him to understand about a very specific skin condition, right? So instead of sending the graduate to a full-on medical school, you give them a specialized cheat sheet or a plug-in module for diagnosing the skin conditions. So the graduate core brain remains unchanged, but they can infer to this highly efficient module when needed. So this is what is happening in LLM, right? We keep the all intelligence of LLM as is and just add some more extra knowledge to it, which is like how to figure it out about a specific skin condition. So that's what is fine-tuning we are doing here in low-rank adaptation. So what's happening here is we take a very small set of new trainable parameters that are attached to the frozen base model. So the whole model or LLM, all the weights are frozen. And we just change and add or basically attach the new weights to the existing model. So how it works? You freeze all the billions of parameters in the base model. You don't change them at all. You insert tiny new layer of weights, the adapters, into the model's architecture. And now during training, you can only update the weights of these tiny adapters, which is much faster and require far less memory. So the result will be you keep the original base model as is. You create a very small adapter file, a few megabytes instead of many gigabytes. To run the specialized model, you load the base model and then apply the small adapter file on top of it. You can have many different adapters for one base model and swap them as needed, one for coding, one for customer support, etc. So it's such a beautiful way to plug and play with your different adapters to change the behavior of the LLM. So how it works, instead of updating the full weight matrix W, W is the full weight of all the metrics in the LLM. And LoRa learns a low rank approximation of the changes in weight delta W here, which is equal to B and A. And B and A are small metrics. So as you can see here, delta W, it is the product of two much smaller matrices. So here, as you can see, only matrices A and B are trained. And during inference, these small matrices can be merged back into the original weight. The new weight will be the old weight plus this B and A, which we have trained. So it is very effective, highly parameter efficient, and crucially has no additional inference latency. So now let's look at these small matrices. Low rank. So what is the meaning of low rank adoption? So as you can see here, there's a matrix of 3 by 3, and the definition of low rank means what is rank? Rank of a matrix is the number of linearly independent rows or columns. Now, what does it mean linearly independent rows? So example, this row is there, 1, 2, 3. Is it completely independent on anybody else? Anything else? Say yes, because this is the first row. Second row, I can see it if I multiplied by first row by 2, then I get the second row. So the second row is not linearly independent. And this third row, it is again independent because I don't see any relationship between any other row. So the rank for this matrix is 2. So that's the definition of low rank. So let's talk about where these matrices A and B come from and how they get initialized. So at the beginning of fine tuning, LoRa initializes A and B randomly. They're just given some number, not much meaningful. And then we start training the model. So during fine tuning, we freeze the original weight of the LLM and we just back propagate through this A and B and we change their weights. And that's the part of the fine tuning. And once the fine tuning is done, now they have new weights. By that I mean now they understand a specific skin condition now. So if we will ask any question about skin to this LLM, it will be able to answer. Now, this delta W, it is inserted in different places. And that's where you will see when you will come to the code, you will see there's one of the parameter called target modules. Q projection, K, V, O, output projection, all this is defined in the code. What actually it is telling us that where to insert this low rank adoption layer in the LLM. So Q projection K and V is key. K is for key and V is for value. And they refer to the query keys and value projection layer within the self-attention mechanism of the transformer model. And LoRa is often applied to these layers as they are crucial for the model's ability to attend to different part of the input sequence. Now, by specifying these layer as target module, you are telling the PEFT method, in this case LoRa, to only add trainable low-rank matrices to these specific part of the model. This significantly reduces the number of parameters that need to be updated during the fine-tuning, making the process much more efficient in terms of computational and the memory compared to the fine-tuning the entire model. So now let's understand what is this Q, K, and V is. So suppose I have this sentence, the old red brick warehouse, which was recently renovated, stores the latest AI servers. Now this is the sentence we are giving it to the LLM. So here you can see the query queue layer. It keeps basically those questions. What am I looking for? Imagine it is a question former layer where it forms the questions. And V layer is what information will I provide if I'm selected? It's keeping the value. It is the content provider. What information will I provide if I'm selected, right? So let's look at this example. Let's focus on how the model understands the word stores without context. Store could mean retail shops. With context, it's a verb and action. The self-attention mechanism is how the model figured this out. So with context, it's a verb and action. The self-attention mechanism is how the model figured this out, that what is the context, whether it's a verb or an action and things like that. So what happened? The step one, first, every word is converted into a vector and embedding. This vector represents the word general meaning. The embedding of warehouse knows about building, storage, etc. The embedding of server knows about computers, technology, etc. But at this stage, the words are just island of meaning. They don't know their specific role in the sentence. This is where the projections come in. So the model now processes the word stores. Its initial embedding is fed into the Q projection layer here. And the Q projection layer is a matrix of weights. Think of it as a question former, as a role specification matrix. It takes the general meaning of store and transform into a specific query vector for the exact context. The new query vector for the store is essentially asking a series of pointed questions to all other words in the sentence. Who or what is performed the action of storing? Looking for the subject. What is being stored? Looking for the object. Are there any words that describe how or when the storing is happening? Looking for modifier. This Q vector is like a specialized detective sent out from the word stores to gather a specific relevant information from the rest of the sentence. Now, let's look at this V projection in action. Simultaneously, every word in the sentence, including store itself, has its embedding passed through the V projection layer. The V projection is another matrix of weights. Think of it as a content provider or an information highlighting matrix. It takes the general meaning of each word and transforms it into a specific value vector. This vector highlights the information that word can provide if asked. So, vector for warehouse. Its value vector could be prepared to answer, I am a place, a physical location, and I am likely agent of the action. It emphasizes its identity as a noun and potential subject. Now let's see what will be the V vector for server. It will be having its value vector would be prepared to answer, I am a thing, server, right? A piece of technology, I am the likely object being acted upon. And same way, you can have V vector for renovated, V vector for red brick. For red brick, the V vector will be, value vector would be prepared to answer, I am a descriptor, a quality of the warehouse. Each V vector is likely a witness statement, pre-written and ready to be read if the detective's questions are a match. Now, putting it all together, that's what attention is all about. The query vector from stores, our detective, is compared against the key vector of all other words. The key projection layer, which we haven't focused on, creates a key vector that acts like searchable tag or label for each word. So the comparison results in high attention score for warehouse and server because they are the best answer to the query's main question: who is doing the storing and what is being stored? So the score for renovated red brick would be moderately high, and the score for the would be very low. The word the, right? So the score for them will be low. Now the model then uses these score as weights, and it takes a large chunk of information from the value vector of warehouse and the value vector of servers and the smaller chunk from the V vector of renovated and red brick. And all this gathered information is combined into a new single vector that represents stores. So the final vector for store is no longer just its dictionary definition. It is now a contextually rich representation that understands store is an action being performed by the warehouse on the server. So now let's connect back to the target modules, right? Q projection and V projection. So the original pre-trained Q projection and V projection matrices are massive and very good at general language understanding. They know how to form general question and provide general information. But when you are fine-tuned it with LoRa, you are saying, I want to teach the model a new specific task like writing in a certain person's style, answering questions about my private legal document, tell me about some specific skin conditions. To do this efficiently, you target Q projection and V projection. So targeting Q projection with LoRa means you are teaching the model how to ask new kind of questions. For legal documents, a LoRa adapter Q projection might learn to create a query vector that asks, what is the governing law clause related to this term? Or who are the parties to this argument? These kind of questions would have known to be asked by the Q layer, Q projection layer. For the same legal document, a LoRa adoption of V projection for the word Delaware would learn to create a value vector that strongly emphasizes I am a jurisdiction, a key piece of information for governing law clause. So by injecting small trainable adapter into these specific projection layer, you are efficiently teaching the model to change how it relates words to each other for your specific task without having to train the entire billion parameter model. And the last thing, we will not go in detail, but just for completeness sake, there's a quantized LoRa is there where basically we take and we just shrink the model. So quantized LoRa, Q LoRa, is basically taking the big model and dramatically reducing the memory usage of it. So you can train a very big model even on a single GPU. Basically, you take the model weights are in, say, 32-bit float. So you load the weight of all the model in 4 bits. So it will cut down the size of the model. So obviously it gives you a massive memory saving and enable fine tuning of like 65 billion plus parameter model on a single 24 GB or 48 GB CPU. So that's what the quantized mean. So now let's look at the code. So as you can see here, the first thing we do is we install all these different libraries, and I already put as a comment what these libraries are all about. This is the parameter efficient fine tuning, a Hugging Face library. This is what is almost industry standard. Everybody is using that. And Unsloth is an optimized library that makes fine-tuning large language model significantly faster and more memory efficient. So that's about Unsloth. After that, before you start your fine tuning, make sure that you are connecting to T4, connected to host T4. This cell is all about emptying the cache because I was running this system again and again. You don't have to do this, so maybe we can delete this. Second is I get this a sample data from Databricks called Dolly 15K. I created another one short because I cut down that data also. This is a massive humanly curated questions answers by Databricks, and this can be used for fine tuning. And this is the file. As you can see, it is have instruction and responses. What is the species of fish, tope or roe? And this is what we are going to fine tune our model on this data. So what we want to see later on, that this data, these answers come as a response from the model after the fine tuning. Here we are not doing much other than just creating a data set. We open this JSON-L file and just created a data set, and we formatted input, context, output. And I'm reading the file, instruction, context, and response, and they just go as input, input, output, output. And then I downloaded this model from Onslaught Fee 3 mini 4K instruction. So this is a Hugging Face page for this model. You can learn more about this model. As you can see, the size is about 2 billion parameters here. And it is built for chat and instruction following tasks, enabling lightweight deployment on smaller GPUs or on mobile devices. So as you can see, this is a small model, very good for trying your fine-tuning task. So here we are giving max sequence length. It is like what is the length of your paragraph. So we are saying 2048, and this length again matters in the sense if you see your example data, if it is too big or too small, then you can play with your sequence length. But I'm leaving it to 2048. No need to change this. Data type, leave it as a auto detection. And now I am just loading the model and the tokenizer as such. Load in 4-bit. This is what is quantization mean, right? We are loading the whole model with 4-bit precision as such. So we can load it in our small RAM and small machine. So as you can see here, I wrote this function from Onslaught applies PEFT like LoRa to your base model. This is what we are telling. And this is rank. Remember, we were doing the low rank adoption. So you give here the rank. And I'm giving here 64. But in the research paper, if you'll see, they will say keeping the rank to 1 or 2 is pretty good. So you can leave it low also, but I tried it with 64 and it's working. This is where the fine tuning comes, right? You will play with these numbers. And again here, target module, we already talked a lot about it, Q, K, V projection, and we are saying put the adapter in these modules, in these layers of transformer, right? Q projection, K projection, and V. So LoRa alpha, actually this parameter controls that how strongly the LoRa module influence the model's output. How much weight you want to give it to the LoRa module. So the typical value can be 4, 8, 16, 32 or so. So there is no one size fit all answer for this. So you will often tune LoRa alpha along with R, which is rank, and learning rate to balance adaptation power or versus overfitting. So as you can see, there's no one size fit all answer. You have to play with this alpha value and rank value and learning rate to balance adoption power versus overfitting. So High, high LoRa alpha means amplify the effect of the LoRa weights, right? Give more importance to the data I am training you on. And lower LoRa alpha dampens the adoption. It's like adjusting the volume of a fine-tuning signal relative to the original one. So that's the LoRa alpha. And then the dropout. In the context of parameter efficient fine-tuning, specifically with LoRa, the LoRa dropout parameter controls regularization during training by introducing dropout into the LoRa layers. And I gave it here 0. So what is the regularization? Because this parameter, the dropout parameter, controls the regularization. So regularization is a set of technique used in machine learning and deep learning to prevent overfitting. That is to help model generalize better to unseen data rather than just memorize the training set. So that is regularization. And LoRa dropout is the dropout probability applied to the LoRa specific weight path during training. We confuse the model while training, we drop out some of the weights. So they cannot be overfitting to the information given to them. That is the purpose. So it prevents overfitting by randomly zeroing out elements in the LoRa modules, activation during training. So higher LoRa dropout, like 0.5%, will aggressively regularize the LoRa adoption, and low value will gently regularize and is more common in practice. So keep it low. So I've kept it 0 here. But again, in the real world, you have to play with these different numbers. Now, this is bias. So in a layer of a neural network, a bias term is an additional trainable parameter that allows the model to shift the activation function independently of the input. So why bias is useful? Without the bias term, a neuron can only output 0 when the input is 0. But with the bias, it can learn a non-zero output. It can learn a non-zero output even when the inputs are 0. How it does all this? Because there's generally an activation functions are there and they shift because of this bias to better fit the data. So this way, the model become more flexible in its prediction. And these biases are also learned just like the weights using the gradient descent when the model is getting trained. So the bias generally left untouched in the original model when we are fine-tuning to reduce the number of trainable parameters. So leave it as none. Again, this is use gradient checkpointing. Unsloth is optimized version. It will checkpoint when it's training, when it feels it's a proper place to checkpoint. Random state. Before we come to random state, let's talk about what is this RS LoRa is equal to false. RS LoRa, it is about rank stabilized LoRa. RS LoRa is rank stabilized LoRa. It's an enhancement over regular LoRa that tries to stabilizing training when using very low rank matrices, small R values like 2 or 4. It does this by scaling and regularizing the low rank updates more intelligently. So if you say true, use RS LoRa true, it applies rank stabilization technique. This can help reduce variance and improve convergence, especially for low resource setting. And if you say false, you are just using standard LoRa without stabilization. So use true if you are using very small ranks like 4 or 8 and notice unstable training or poor conversions. Use it, make it true. But for higher rank like R64, setting it to false is usually fine. So I'm leaving it as false. And this low FTQ stands for low rank fine tuning with quantization. Fortunately, we already understand what is quantization. So this is a method which combines LoRa parameter efficient fine tuning with quantization aware training, which allows you to fine tune a quantized model like 4-bit or 8-bit. So I'm leaving it none, so no quantization aware fine tuning is applied here. And you are assuming the model is either not quantized or quantization is handled separately. So that's that. And now let's look at what is the random state. And then random state is nothing but it's just a seed to create the random numbers in this whole file. Okay, making only a small portion of the model trainable for efficient fine tuning, because as you can see, we have defined all this here. Now let's see training the argument optimized for onslaught. So if we'll go through everything, you can see there's a model, tokenizer, data set, and sequence length. We talked about data set number of processes, like how many data set per proc it should run. So it depends on how big a machine you have, you can change that. Per device train batch size, I kept one. Again, this number you can play with. When I put higher number, I was getting error. So there was some issue with my system setting with the GPU and RAM I have. So gradient accumulation steps parameter is a technique used during the training of deep learning models, especially when dealing with large models or limited GPU memory. So how it works is when you train a neural network, you typically process data in batches. So the gradient, which will tell the model how to adjust its weights, are calculated for each batch. And then the model weights are updated based on these gradients. So a large batch size generally provides a more accurate estimate of the true gradient, leading to a more stable and potentially faster training. However, a large batch size requires more GPU memory too. And then this accumulation process. So there's a large batch size and then the accumulation process. The accumulation steps allows you to simulate a large effective batch size without increasing the memory required for a single batch. So instead of updating the model weight after processing each mini batch, the gradient form multiple mini batches are accumulated, and then the model weights are only updated after the gradients from a specified number of accumulation steps have been collected. So what's actually happening in very simple way, simple English, that it will update the gradient weights only after completing the batch of 8. So in essence, gradient accumulation step is a trade-off between memory usage and computational time. Again, something you should play with to learn. So warm-up steps. So warm-up steps parameters is related to the learning rate scheduler used during training. It's a technique to gradually increase the learning rate at the beginning of training instead of starting with a high learning rate. So you understand what it's saying? It's saying that gradually you increase the learning rate. So here we gave 5 means that over the first 5 training steps, the learning rate will be gradually increased until it reaches the specified learning rate, which we gave here 2e power of 4. So that is the learning rate. So it will take 5 steps before it will reach to the learning state. So that is what it is. So by using the warm-up period, you can often improve the stability of training and help the model to converge to a better solution. Again, no hard and fast number, but you can play with different numbers here. Number of trainings, how many times you should train. Again, this is a big variable. You have to play with this to get a proper fine-tuned model. And learning rate, again, same thing. This is all figuring out what machines are supported. Slogging step is again about logging. not very important for me at this time. So this is about optimizer, like what algorithm to be used to optimize the training. So I don't think you should be changing this algorithm for optimizer, but there are multiple options available for you. If you feel you can read more about it and you can get it changed. So next is weight decay. It's a regularization technique used during a training of neural network to prevent overfitting. So in regularization, overfitting happens when a model learns the training data too well, including the noise and specific details that are not representative of new unseen data. This leads to a poor performance on validation and test sets. So regularization technique aim to add constraint or penalties during training to discourage the model from becoming too complex and to improve its generalization ability. So that's what the regularization does. So the weight decay adds a penalty to the loss function that is proportional to the square magnitude of the model's weight. The larger the weight, the higher the penalty. So this weight decay parameter controls the strength of this penalty. A high value means a stronger penalty for a larger weight. And an optimal value for weight decay is typically found through experimentation and can depend on the model, data set, and other hyperparameters. So again, you just do the fine tuning, and then you see if the fine tuned model is too much overfitting for your training, then maybe you have to come and change this decay number to see how it works out. And this learning rate scheduler type linear, by that it means how to change your learning rate. It's a linear. After warm up, it's linearly, it will increase. Other option can be, cosine, constant, polynomial. Again, this is very esoteric word of machine learning where we are getting into changing this learning rate from linear to cosine and all. You will never know what is the right number unless until you have to train, play with again and again, and then you will realize, because it is affecting the learning rate, and you have to figure it out. You have to train the model and see how things are, and then you can change this number. So start with linear. And then, of course, seed is again giving a random seed. Output directory save strategy means every after one epoch it will save it. And nothing very special here. Number of workers, again, depends on how much memory you have. So I will say don't pin the memory and change this number of workers accordingly. You just go ahead and you train the model. So once the training is done, I wanted to see how it is behaving for my questions, because now I trained the model with my data set. So this one, why can camels survive for long without water? So when I fire this question, I do see it talks about they can store fat in their humps, which can be metabolized with water. This line was not there when we were checking initially. So now my training is complete. I wanted to test. So this is another question I'm asking. Alice's parents have three daughters, Emmy, Jessie, and what's the name of the third daughter? So that's the question I asked my this fine-tuned model, and it's given me the answer exactly as it was told in the fine-tune. So look at here. So let's search Alice. Response, the name of third daughter is Alice. So you can see this new model has learned. Now another question I was asking about Jefferson. Who is Thomas Jefferson? And the context is this. And let's see the reply we got. Here is the response, right? April 13, 1743 to 86 was an American statesman. That's in my text. And when I asked this, it did reply exactly that was an American statement. Before, when I asked the same question, it did not reply to me in a very similar manner. See, it was replying this way. So now it proves that after the training, after the fine tuning, it starts picking up the information from the new data. So that's good. Now you can take this model and save it. So you can use it in Olama or anywhere else. And this is the code to download this model after saving. So that's it. Hopefully it will be of some help. We did a very quick hello world of fine tuning a model. And obviously it needs a lot of trial and error and figuring out the right values to make sure everything is working the way it is working. As you can see, you can fine tune a model in few minutes here. But in reality, in real life, when you're doing this, you have to play with this parameters and keep doing it again and again and testing and making sure that everything is working. That is, I feel, 3x to 10x of your development effort, the testing of this model and how it's responding to your queries. So that is the important thing here. Okay. So let me have your feedback and let me know what else you would like to see on this channel.